Yes, we can hear you. Let me just get your slides up and then just say, oh.
Yeah, and so the next presentation is Dante Lauretta with the update on the Osiris-Rex mission.
All right, thank you.
Go ahead, Dante.
Yes, been an exciting period for Osiris-Rex. I've got a lot of things to talk about, so I'll jump right into it with the next slide, please. So just as a reminder, Osiris-Rex has a very capable payload suite. The data that you'll be seeing today is primarily from the OCAM set of imagers. That's the Polycam narrow focus imager, the MapCam color mapping imager, and not much from the SAMCAM, the wide angle camera for documenting sample acquisition. We'll also see some data from OVIRS, our visible and infrared spectrometer, and OTES, our thermal emission spectrometer, as well as just check out reports on the laser altimeter OLA and the student-led X-ray imaging spectrometer REXIS. Next chart. This is a reminder of the overall Osiris-Rex mission timeline. We launched in September of 2016, executed an Earth gravity assist to do the inclination plane change onto Bennu's orbit in September of 2017, and started the approach phase in August of this year. Nominally, we'll be at the asteroid until March of 2021, and the samples are due back on Earth in September of 2023. The next chart gives a more detailed timeline of the operational profile. So the approach phase began on August 18th, 2018, when we got the first optical acquisition images with the Polycam. We executed a series of approach maneuvers, which I'll show you in a little bit here. Arrival, we marked on December 3rd of 2018 when we fired the engines to begin a series of hyperbolic flyby over the North Pole, Equator, and South Pole in what we called our preliminary survey. And then we went into orbit around the asteroid on New Year's Eve of this year, and we're currently in the orbital A phase. We'll be moving on to the actual science campaign, what we call the site selection campaign, in late February, when we leave orbit for a series of survey stations at different imaging conditions for characterizing the detailed morphology of the asteroid surface, and as well as spectral mapping optimized for OVIRS and OTIS instruments. The sample acquisition campaign is scheduled to begin in late 2019, and the touch and go sample acquisition event marked there as the tag is nominally scheduled for July of 2020. Next turn. Next slide. So this is our graphic that the Communication and Public Engagement Group put together to kind of demonstrate the maneuvers that took us from our initial approach velocity of 491 meters per second relative to Bennu down to our orbital insertion velocity of 5 centimeters per second. So we executed a series of asteroid approach maneuvers, which dropped us down sequentially, initially down to 140 meters per second, then down to 5.3 meters per second, then to 11 centimeters per second, and 4 centimeters per second, and then we picked up that last little velocity as we did the orbital insertion maneuvers to start the preliminary survey phase. Next chart. So one of the key objectives of the approach phase was to survey the asteroid environment for any operational hazards. So in addition to a dust plume search, so as some of the earliest observations in late August and early September were to look along the orbital track and along the anti-sunward direction of the asteroid to see if Bennu was showing any signs of activity that would have expressed itself as a dust trail or an ion trail. And we didn't see any evidence of that in the approach phase data. We also did a natural satellite survey with detection limits down to 8 centimeters within 300 meters of the asteroid center. So phenomenal job by our asteroid astronomy working group led by Carl Hergenrother. There was no signs of any co-orbitals around the asteroid. Next chart. So we benefited enormously from an extensive ground-based astronomical campaign to characterize the target asteroids. Some of the most useful data were acquired by the Arecibo planetary radar system, so I brought those up there to remind you of what we expected going in. And then this next chart shows you what we actually saw during the approach phase to the asteroid. And as you can tell, bottom line is the radar reconstructed three-dimensional shape model did a phenomenal job of predicting the shape and topography of the asteroid for us. So this is a really great validation of the radio astronomy techniques for characterizing asteroid shapes and morphologies. The biggest uncertainty was in the z-axis along the rotation pole. Bennu's a little bit squatter than we expected, but well within the uncertainties that we had provided from the ground-based radar data. So this is really good news for the mission because we designed the whole observing profile, orbital insertion, as well as those detailed survey stations and our lower altitude recon and ultimate sampling events around this shape. So it's really good news that we got it so right and that all of our mission design plans are valid as we move forward. Next chart. One of the most interesting aspects of the asteroid is the wide range of albedo variations. So over there on the left, I'm showing you MapCam color composite data. RGB, R is the W filter, the astronomical W filter, such as is used in the 8-color asteroid survey. The green filter is a V-band, and the the B is a B prime filter. It's similar to the B filter from the ECAS filter set, but shifted a little longward just to catch a better detector response for our sensor on the MapCam. And then over on the right is a similar polycam frame taken at same kind of imaging conditions. So note the very low phase angles of 5 degrees here. And you can see the field of view difference. Basically, MapCam has about a 10 times field of view with a polycam, so you get degraded resolution as a result of that. So looking over at the image on the right, we were immediately struck by the very dark spot down there in the lower southern hemisphere. And when I talk about hemispheres, I'm referring to the rotation state. So the plus Z axis, i.e. the right-hand rule for rotation, is up in this image. Bennu is a retrograde rotator, so that actually is in the southern celestial hemisphere. So more accurately, the dark spot's in the minus Z hemisphere of the asteroid. That has an albedo of about 3.4% geometric albedo. We do see a range of albedo variations. The average geometric albedo across the surface of the asteroid is 4.4%. And we're seeing a substantial population of reflectances and geometric albedos around 7%. And currently the brightest object observed on the asteroid surface has a geometric albedo of at least 15%, but it's not fully resolved, so that value may increase as we get higher resolution data and get a better understanding of the true geometric albedo properties of that brightest material. This is really diverse and unexpected for a primitive asteroid of this nature. Much more diversity in reflectance than we're seeing, for example, on Ryugu from the Hayabusa 2 mission, and more similar to what we saw in terms of the albedo variations on 67P, the target of the Rosetta mission. So there was a lot of interest in the very dark material, since the primary objective of Osiris-Rex is to return carbon-rich and hydrated material. So we have taken a look at the composition of the dark spot, at least with the MapCam color filters, and we are seeing an absorption at 0.55 microns, which we are tentatively assigning to magnetite, the iron oxide. Next chart. This is just showing you a Polycam 12 image mosaic taken right before the arrival. So this is currently the highest resolution data set that we've obtained on the asteroid. We're not imaging with Polycam during the preliminary survey phase or orbital A phase for data volume reasons and operational reasons. We'll be back to Polycam imaging when we enter into the detailed survey campaign at the end of February. So right now we're getting resolutions of about 33 centimeters per pixel. This is a high phase angle image taken at a phase angle of 48 degrees, so it's really showing you some of the topographic features. Some of the things that jump out at us right away from the asteroid surface are the large boulders. The one down there in the lower right was expected and seen in the radar data. That was the only feature that was really observed from that data set, so we were actually not expecting a large number of boulders on the order of 10 meters or so. In our initial boulder census population, we've got over 200 boulders in that size range. We are looking at a pretty rough and rugged surface, more so than we expected. Some smooth areas are apparent. So for example, right along the equator and just off to the east, you can see a small impact crater about 20 meters in diameter. That looks like it may have apparently boulder-free material. We cannot tell the grain size at this point because we're looking for things on the order of centimeter scale, and our resolution isn't quite there yet. We do have the expected so-called spinning top shape, which seems to be characteristic of a subset of the near-Earth asteroid population. However, we thought that the equatorial region would have a much more pronounced ridge structure, kind of like we're seeing on Yugu. Bennu's ridge is much more muted. There are a large number of impact craters. You can see one all the way over there on the equator on the eastern view of what we're looking at here. And there are impact craters at least up to 150 meters in diameter and maybe a dozen or so large impact craters that are apparent on the surface of the asteroid. So we're thinking that the asteroid surface cratering age may be older than we expected and may obviously record its collisional history in the main asteroid belt. That dark spot that was apparent in the previous image is down there just a little bit south of the equator and all the way over on the left side of the image. That is some sort of outcrop. We think that may be on the order of 100 meters in total extent and may represent kind of the building blocks of this asteroid. Overall, the shape and morphology are consistent with our ground-based expectations. The surface is more rugged, the boulder population is more substantial, imaging that was acquired in preliminary survey, our stereophotoclinometry team went to work to produce the Bennu shape model. As I mentioned, Bennu has the expected spinning top shape. I'll show you in a chart or so where we were able to use those hyperbolic flybys to get the mass of the asteroid, and as well as combining that data with the spectral link to the CI and CM chondrites. We do think Bennu is a rubble pile asteroid. And if we use the bulk particle density of those meteorites, we're looking at a macro porosity between 25 and 50%. Obviously, the prominent surface boulders are expressed in the shape model. We are seeing a series of high-standing ridges. So if you look at the image over on the right at the north plus Z view, you can see that there are some ridges that are extending down towards the equator, even in past the equator and down into the south. At the American Geophysical Union, we reported that there might have been a polar wobble, and it turns out that, in fact, instead of a wobble, there's a significant center of mass, center of figure offset in the plus X direction. So the pole, it was off as we were trying to go through our rotational solutions, which made it look like it's wobbling. So once we realized that it was actually just a COM-COF offset of 1.3 meters, all the solutions converged, and we no longer can detect a wobble at the 0.2 degree level. Next chart. So we did get OLA on in preliminary survey. This was really an instrument checkout period for us. We got over 3,000 range measurements at just over 7 kilometers. 7 kilometers was the design constraint on OLA, so it was right at the outer range of its operating capabilities. So really this was used to confirm the navigation that we were hitting the close approach distance of 7 kilometers that we were targeting, and we got that very well. And then we were able to overlay the OLA returns on the SPC-derived shape model and confirm that that shape model was highly accurate with scale errors about 0.5% in just a few of the axes, and that's been worked out as we've gone through more rigorous shape modeling efforts. So OLA is operating nominally, and we're looking forward to detailed shape modeling efforts from that instrument when we get into our orbit B phase later this year. Next chart. We did our radio science experiment during those hyperbolic flybys, so we're able to constrain the mass of the asteroid, as you can see there, about 73 billion kilograms. Combining that with the volume is where we constrain the bulk density of 1190 plus or minus 24 kilograms per cubic meter. That's very consistent with what we had determined from the ground, so that's an exciting result. Steve Chesley had a paper in 2014 reporting the detection of the Yarkovsky effect on the asteroid from orbital measurements extending from 1999 to 2012. He estimated a bulk density of 1260 plus or minus 70, so we were right at the 1 sigma level of his estimate, and this really shows that you can use precise astrometry combined with thermal modeling from a Spitzer-like infrared telescope, as well as spin and shape data from radar or photometry to do physical characterization of near-Earth asteroids at this level. So this was great for us for mission design, but I think it also has implications for planetary defense. Obviously, the mass and the density of a potential Earth impactor is a very important parameter to constrain, and we have now validated this first-of-its-kind technique to use the Yarkovsky effect detection along with this radar and infrared astronomy data set to get that important information. Next chart. So then we got into orbit on New Year's Eve. Bennu is currently in orbiting with an average distance of 1.58 kilometers. It's in an eccentric frozen orbit. It's very stable and very well behaved. We're going out to about 2.1 kilometers. We have a couple of world records that we've set here in planetary spaceflight. Bennu has now become the smallest planetary body ever orbited by a spacecraft, and Osiris-Rex has achieved the closest orbit of any body by a spacecraft from Earth. So the orbit phase is not really a science campaign phase. It's primarily there for the navigation team to transition from using star fields to landmarks on the asteroid surface That transition is going very well, and we're achieving the navigation accuracies that are required for us to depart orbit in about 4 weeks and begin the detailed survey campaign of the mission. Next chart. So right now we're just doing optical navigation imaging. So we're using the nav cams. These are very wide field of view cameras. The shape modeling team has produced a series of landmarks for the flight dynamics team to use. They're doing a great job registering those. The whole system is shaping up very nicely. In addition to the primary group led by Goddard Space Flight Center and Kinetics Aerospace, there's a backup shape modeling team at JPL. Those solutions are in very good agreement with each other, and the navigation team is confident in their ability to transition over to landmark tracking optical navigation. And next chart. And one of the other activities that we've done in flight so far is to deploy the TAGSAM. That is the 3-meter long robotic arm that you can see over in the artist conception of the spacecraft there on the left. That was secured in a launch container and also bolted to the spacecraft bus for launch, and we kept it in the launch container just to keep it clean as we were doing the large maneuvers on the main engines. But we successfully deployed that launch cover in October, released all the separation bolts, and we have deployed TAGSAM into its sampling configuration as well as other configurations. And the image over there on the right is a SAMCAM image of the TAGSAM head. You can see the 24 circular contact pad samplers that are on the base plate of the sample head. So we've bent the wrist, used the wrist motor to articulate the bottom of the sample head. So what you're seeing here is actually what will contact the asteroid surface. And then if you look closely, just off center to the right of the TAGSAM, you'll see a shadow of the screen that surrounds the outer edge of the TAGSAM filter. So that is exciting because if we can get a similar image after sample acquisition, I hope we'll see outlines of regolith particles getting visual confirmation that we've successfully collected a sample. So that is my whirlwind tour of the status of the Osiris-Rex mission. I may have time for one very quick question. I do have a meeting I need to get on to.
Okay, questions? Thank you, Dante. Questions from the room or online? Okay.
Oh, yeah. Dante, question from online. Do you have a bulk albedo?
Yeah, the bulk geometric albedo is 4.4%.
Okay, thank you.
Okay, thank you very much, Dante.
All right, thanks. Take care, guys.
Okay. Okay, so